How do we break the tyrannical grip of Earth's gravity without riding controlled explosions into the sky? For decades, chemical rockets have been our only bridge to the cosmos, but they are brutally inefficient, consuming vast amounts of fuel just to lift their own weight. Imagine instead a physical highway to the stars, a colossal ribbon stretching from an anchor point on the equator, piercing the atmosphere and extending tens of thousands of kilometers into the dark void of space. This is not science fiction, but a profound engineering challenge that could fundamentally alter our future. The concept of a space elevator relies on a breathtakingly elegant application of classical physics. At its core, the structure is a tether anchored to the Earth's surface and extending outward past geosynchronous orbit, a specific altitude of roughly 35,786 kilometers, where a satellite's orbital period perfectly matches the rotational speed of our planet. By extending the tether well beyond this point and attaching a massive counterweight, the entire system is kept taut. It behaves much like a ball being spun on a string, utilizing the rotation of the Earth to maintain its monumental vertical posture. This delicate balance of orbital mechanics pits gravity against centrifugal force. Below the geosynchronous node, gravity pulls the tether downward toward the planet. Above that precise altitude, the centrifugal force generated by the Earth's rotation flings the counterweight outward into the immense depth of space. The opposing forces create a state of immense tension, pulling the ribbon perfectly straight. Vehicles, often called climbers, could then mechanically ascend this taut cable, carrying payloads into orbit using a fraction of the energy required by conventional rockets. Yet bringing this elegant physical model into reality introduces one of the most daunting material science challenges in human history. The sheer scale of the forces acting upon a 100,000-kilometer cable requires a material with unprecedented tensile strength, which is the maximum amount of stress a structure can withstand while being stretched or pulled before it breaks. According to data from NASA and independent engineering studies, no conventional material like steel, titanium, or even Kevlar comes close to surviving the immense gravitational shear and centrifugal tearing forces. They would collapse under their own immense weight long before reaching orbit. To bridge this impossible gap, scientists theorized the use of carbon nanotubes as the primary building block for the elevator's ribbon. These microscopic cylinders of carbon atoms, arranged in a hexagonal lattice, possess a tensile strength up to 100 times greater than steel at a fraction of the weight on a molecular level. The carbon-to-carbon bonds are among the strongest chemical connections in nature. If woven into a macroscopic thread, a cable no thicker than a pencil could theoretically suspend the weight of fully loaded commercial aircraft without snapping. However, moving from microscopic miracles to megastructure reality represents a monumental leap in manufacturing. Currently, engineers can only grow pristine carbon nanotubes to lengths of a few centimeters. The challenge lies in creating continuous defect-free strands that span tens of thousands of kilometers. A single missing carbon atom in the lattice can create a microscopic stress fracture, compromising the integrity of the entire ribbon. Scaling up this production requires revolutionary breakthroughs in nanotechnology and automated molecular assembly that we are only just beginning to conceptualize. Those initial material constraints still inform every design decision, but the potential payoff justifies the immense research investment. If we can successfully deploy a carbon nanotube tether, the economics of space access will undergo a paradigm shift. Currently, launching a single kilogram of payload into low Earth orbit costs thousands of dollars. A functional space elevator could slash that cost to mere tens of dollars per kilogram. This dramatic reduction would suddenly make massive orbital solar farms, large-scale orbital habitats, and deep space assembly yards economically viable. Beyond the tether itself, engineers propose deeply complex designs for the climbers that will ferry cargo and passengers to the stars. These mechanical vehicles cannot carry heavy chemical fuel, as that would defeat the elevator's primary purpose. Instead, they must rely on external power sources to ascend the ribbon, supplying gigawatts of electricity to a vehicle climbing through the upper atmosphere and into the vacuum of space, presents a formidable logistical hurdle, requiring power transmission technologies that far exceed our current electrical grid capability. The leading solution for this ascent involves advanced laser power beaming. Ground-based installations or high-altitude solar platforms would fire highly focused beams of light at photovoltaic arrays mounted on the underside of the ascending climbers. These specialized solar panels would convert the intense laser energy directly into electricity, driving the mechanical treads gripping the ribbon. Research published in Advanced Aerospace Journal suggests this method could provide continuous clean power, propelling climbers at speeds of hundreds of kilometers per hour toward the geosynchronous terminal. As these climbers ascend, they will enter an increasingly hostile environment. The space elevator will be a massive, stationary target in a very crowded orbital highway. Low Earth orbit is currently littered with millions of pieces of space debris, ranging from flecks of paint to defunct satellites, all traveling at staggering velocities of over 28,000 kilometers per hour. A collision with a piece of debris the size of a marble could unleash the kinetic energy of a hand grenade, threatening to sever the tether and cause a catastrophic collapse. To mitigate this orbital gauntlet, the tether cannot be a simple, rigid string. It must be designed as a wide, curved ribbon, perhaps structurally woven like a net, allowing small micrometeorites and debris to punch cleanly through without compromising the overall load-bearing capacity. Furthermore, the equatorial anchor station would need the ability to physically move by slowly shifting the base station across the ocean surface. The entire ribbon could be gently swayed like a blade of kelp in the tide, actively dodging larger tracked pieces of space junk. This brings us to the monumental scale of the Earth-bound infrastructure. The anchor point, often referred to as the Earth port, must be a marvel of marine engineering, positioned near the equator to maximize the rotational boost and minimize the risk of severe weather. This floating megastructure would dwarf the largest oil platforms. It would serve as a bustling international hub, a massive seaport, and an aerospace terminal, coordinating the delicate dance of ascending climbers while managing the immense tension anchoring the ribbon to the planet. Yet even at the serene equatorial latitudes, the lower atmosphere poses severe threats. The first 20 kilometers of the tether must survive the violent forces of the troposphere. Hurricanes, jet streams, and intense atmospheric shear will constantly batter the ribbon. Furthermore, the cable itself will act as a colossal lightning rod, stretching through highly charged storm systems. The materials science must account for not only tensile strength, but also extreme electrical conductivity, finding ways to safely ground millions of volts of atmospheric electricity without frying the ascending climbers. As climbers push through the atmosphere and into the vacuum, their movement introduces complex dynamic forces into the system. The Coriolis effect, a consequence of the Earth's rotation, will push laterally against the climbers as they ascend, causing the massive tether to bow and vibrate. Much like plucking a guitar string, the movement of payloads will induce harmonic oscillations that travel up and down the 100,000-kilometer length. Unchecked, these low-frequency waves could amplify, violently whipping the tether and tearing the anchor from its ocean moorings. Managing these extreme oscillations requires a symphony of active damping systems. Engineers propose outfitting the climbers with variable speed thrusters and intelligent suspension systems that adjust their ascent rate in real time, deliberately moving out of phase with the tether's natural frequencies. Additionally, the counterweight in deep space could act as an active mass damper, shifting its center of gravity to absorb and neutralize the harmonic waves. The entire elevator would function as a living, breathing cybernetic organism, constantly adjusting to the chaotic forces of the cosmos. The realization of such a megastructure transcends the capabilities of any single nation or corporation. The construction of a space elevator demands unprecedented global cooperation, pooling the intellectual, financial, and material resources of humanity. International treaties would need to be rewritten to govern the airspace and orbital lanes surrounding the tether. The economic integration required to fund a project estimated in the trillions of dollars would foster a new era of resource management, aligning global industries toward a singular transcendent objective: Once operational, this orbital highway will fundamentally rewrite the rules of space exploration. Without the crushing gravity penalty, we can begin assembling massive interplanetary vessels directly in orbit. Components for deep space habitats, heavy fusion propulsion systems, and vast solar sails can be lifted piecemeal and constructed in the weightless environment. The space elevator becomes a shipyard in the sky, serving as the staging ground for missions to Jupiter, Saturn, and the distant reaches of the Oort cloud. The principles established here are not confined to our pale blue dot. When we cast our gaze outward, the physics becomes significantly more forgiving. Consider the Moon or Mars. The gravitational pull of these celestial bodies is a fraction of Earth's because of this lower gravity. The tensile strength requirements for a Martian or lunar space elevator drop dramatically. In fact, materials we currently manufacture in bulk, like Kevlar or Xylon, possess enough strength to build a functional elevator on the Moon today. On Mars, the engineering landscape offers a unique, ready-made advantage. The planet's inner moon, Phobos, orbits remarkably close to the Martian surface. Engineers propose that Phobos itself could be captured and utilized as the ultimate counterweight by anchoring a tether to the Martian equator and extending it upward to a station orbiting in tandem with Phobos. We could establish a permanent, low-energy supply line to the red planet. This would accelerate the colonization of Mars, transforming it from a distant outpost into a thriving second home. The echoes of those initial theoretical hurdles persist, driving a relentless pursuit of perfection in our laboratories. Even if a terrestrial space elevator remains decades away, the pursuit of the necessary supermaterials is already revolutionizing other fields. The quest for flawless carbon nanotubes is accelerating advancements in battery technology, biomedical engineering, and lightweight aerospace composites. The dream of the elevator acts as an immense catalyst, pulling human innovation forward even before the first kilometer of ribbon is ever cast. And our material horizons continue to expand. While carbon nanotubes remain the gold standard, scientists are actively synthesizing alternatives like graphene ribbons and boron nitride nanotubes. Graphene, a single layer of carbon atoms arranged in a two-dimensional honeycomb lattice, offers extraordinary tensile strength and electrical property. If researchers can develop techniques to seamlessly stitch immense sheets of graphene together without edge defects, it could provide a viable, perhaps even superior, alternative to the cylindrical nanotube structures, offering a wider, more resilient ribbon against orbital impacts. Ultimately, conquering the engineering and material science challenges of the space elevator represents a critical evolutionary threshold. It marks the transition from a species that merely visits space to one that permanently inhabits it. By replacing the violent, explosive brute force of chemical rockets with a silent, steady ascent along a carbon thread, we fundamentally alter our relationship with the cosmos. The prohibitive barrier of gravity, which has kept us confined to the surface of our birth world for millions of years, finally dissolves. We stand on the precipice of a new frontier, looking up at the sky not as an impenetrable ceiling, but as an open door. The space elevator is more than a megastructure. It is the physical manifestation of human ambition, a testament to our relentless desire to build, to explore, and to reach beyond our grasp. When that colossal ribbon finally stretches from the ocean to the stars, it will carry not just cargo, but the boundless future of a truly spacefaring civilization.